Base draft, an Emission Engineering product. Hi and welcome to Emission Engineering. Today we will remind you how important draft measurements on fired heaters are. First of all, have a look what API recommends, how and above all where the draft should be measured. Well, API 556 is pretty clear in that. Draft should be measured in 4 locations. Location 1 is near the heater floor. Location 2 at the bridge wall. Location 3 downstream the convection section but still upstream of the stack damper. And location 4 downstream of the stack damper. These 4 locations are recommended and implemented since decades, but unfortunately lost importance since pressure transmitters has been becoming the normal way to measure draft. The obvious advantage of transmitters is that you can read the values from remote and you can put them into your alarm or interlock strategy. As a consequence, nowadays most fired heaters are equipped with only one transmitter, most often in location number 2. It is there at the bridge wall because looking at a typical draft profile inside a heater, you will see that location 2 is the spot where the lowest draft, the highest absolute pressure respectively, can be measured. The recommended value as per API is -1 to -3 mm of water column or -0.1 to -0.3 millibar. Most refineries didn't see the added value in putting 4 transmitters in all 4 locations. Therefore, most of them simply abandoned the opportunity to measure also the other 3 locations. Another reason why already existing installations for the draft were abandoned in the past is that the measuring devices were not reliable. Most furnace manufacturers supplied in the past as their standard burden-type pressure gauges, like those shown here. Everybody that has been working with those on low pressures know that a little kick over the range makes the gauge offset already. So when the bridge wall gauge was replaced by a transmitter, the existing gauges were abandoned and operator didn't pay any attention to those 3 measurements anymore. In our experience, the ideal device to measure draft while staying with analog instruments are incline manometers. When picking the right measuring range, they normally don't need maintenance, and if so, in a couple of minutes they are reset for measurement again. Furthermore, putting them into a system with adequate valves, calibration or steering only takes a few seconds. Okay, we learned so far. Draft measurements can be made user-friendly. What brings us to the question, what is the added value of having 4 measurements instead of only one, the one at the bridge wall? Let's go step by step. The draft at the floor of the furnace have a significant importance, because for natural draft burners, the size of the burner itself depends on that value. As an example, let's say a furnace vendor estimated to have -10 mm water column at the floor of its heater, then he would buy burners in such way that the burners would let pass the amount of air required at that draft level. The amount of air can be derived by the maximum heat release, design excess air, and ambient air conditions. Let's take an example. A burner should fire 2.5 MW at 15% excess air and in normal operating or normal ambient conditions. As a thumb rule, 1 MW requires approximately 1000 norm cubes per megawatt at stoichiometric conditions. So the air required is 2.5 times 1000 times 1.15 makes 2875 norm cubes per hour. If your burners are correctly sized and you want to operate under those conditions, 2875 norm cubes passes the burner throat when the draft at the heater floor where the burner is installed has -10 mm of water column and the air dampers are fully opened. So if you don't measure the draft at that point number 1, you can only derive the pressure at the floor from the measurement indirectly from the draft at location 2. As a thumb rule, the draft increases with the height of the radiation section by 1 mm of water column per meter of elevation change. Example: If you have minus 2 mm water column at the bridge wall and your radiation section is 8 meters high, you can estimate that the draft is approximately minus 10 mm water column there. But it is always better to measure it, as the thumb rule works for flue gas temperature of approximately 800 degrees C at the bridge wall. For lower temperature, it may be lower. Another asset is to physically see changes or oscillations in the value of the draft. The first video shows a normal oscillation, often to be observed in fired heaters. The second one could indicate a burner flame to be or to go unstable, more evident in location 1 compared to location 2. Besides, draft oscillations, as just seen, indicate often that the flame is huffing. Huffing is a noise from the flame that is recognizable by an experienced operator. True is that this noise is more easy to recognize on a heater with a single burner, like on a burner test rig. On multiple burner applications, the effect can be less obvious. Nevertheless, the likelihood of determining flame instability increases if the draft is measured also in location 1. The good thing with those incline manometers is they cannot be cheated. They will display any change in the pressure conditions, unlike most transmitters. Transmitters often have attenuation factors incorporated, or end users flatten their signals by other means. Another plus of measuring in location 1 is that you can cross-check whether a furnace vendor has correctly calculated the draft profile. We already mentioned that the most important spot for a draft measurement is location 2. If one is able to keep the negative pressure just slightly below zero, the Tramp air, also sometimes referred to as undesired air ingress, is minimized. Tramp air could only be avoided more by operating on positive pressure, but this is something not recommended by API due to safety reasons. Any millimeter of water column you operate on too high draft will increase the amount of Tramp air. For example, operating instead of minus 2 mm of water column on 4 mm water column increases the Tramp air by 41%. Remember, flow rates change by the square root with pressure. So in our case, the square root of 4 divided by 2 is 1.41. Very valuable is also to observe the draft readings in location 1 and 2 with inclined manometers and comparing those to any transmitter that might be installed. Most likely you will observe draft to be less steady than transmitters suggest. You also have a reliable backup for your transmitter in case he has some malfunctions. This brings us to location 3 of our draft measurements. It is downstream of the convection section. Comparing the pressure there, the pressure drop of location 2 and 3 respectively over time, can indicate when the convection section may start plugging. This can be due to refractory fall on the convection section, excessive scale on the tube or fins, or other obstruction reasons. A rise in the delta P from location 2 to 3 is definitely something you want to be aware of, something you won't if you measure only at location 2. We had a customer puzzling why he was not able to get more draft, thought the stack damper was fully open. He could just achieve a slightly negative pressure in location 2, but at worse weather conditions like wind and rain, he was urged to bypass the PLC trip on high firebox pressure in location 2. Additional temporary measurements in location 3 suggested the convection section causing too high delta P. In the next turnaround inspection of the convection section from below didn't reveal any problem neither. But finally the convection section was inspected from the top, and it became obvious that refractory had fault on the tubes, increasing the pressure drop like you can see on the photo. Location 4 is measuring the draft downstream of the stack damper. For those heaters that have no stack damper, the measuring point might be also upstream of the ID fan on a balanced draft system. The draft of location 4 tells if you are still able to send the flue gases to the stack and if your stack damper has the right characteristics to control your draft properly. This location 4 also becomes valuable to know in case there's a common stack for several heaters. Such systems often have a common heat recovery device and an ID fan for conveying the flue gas to the stack. The stack damper of each furnace controls the draft at the bridge wall. Here you can see the system under normal operating conditions. The furnace low may vary, as it is often the case. The draft in the flue gas duct is moderate, here approximately minus 40 mm of water column. So far, no problem. In case of trip of the heat recovery system or the ID fan, the situation may change dramatically. The flue gas bypass to the stack is opened and he is normally not designed for controlling the draft upstream. As one can see, the draft level can go up significantly. That forces the 3 stack dampers to close more and may run to problems in one or more furnaces. Here furnace number 1, the one that operates on low load, cannot maintain the normal draft level anymore, as the stack damper cannot be closed more, due to a minimum mechanical stop. As a consequence, Tramp air will increase, and until burner dampers are readjusted, also the excess air will go up. It becomes evident that it is very important to know the control possibilities of your stack dampers by measuring draft in locations 3 and 4 before you are getting in such a scenario. A few words to draft measurements on very big heaters. In former times, furnace vendors had foreseen measurements in more than just the 4 locations. Our base draft device can of course also accommodate more measurements than just 4. There is literally no limit. Okay, now as you know why draft measurements in those 4 locations are useful, we give you some more details in how our base draft device looks like. The standard device has in total 4 draft measurements, 2 doubled incline manometers with different scales according to the individual conditions of your heater, very similar to those you saw in the videos earlier. The manometers are built into a small cabinet typical for field instrumentation. Below the panel there is a valve attachment plate. With the help of those valves, the manometers can be zeroed whenever this is desired. It only takes a few seconds, as you can see on this short video. Cabinet and attachment plate are attached to a post, and that post fixed on the ground. Other ways of attachments like wall installation are of course possible. The filling oil used for the manometers has specific properties that avoid easy evaporation in summer and freezing in winter. Once filled up, it can run for years without any maintenance. All handling can be done without special tools and without unpiping. The only thing that a client has to do is running 12 mm stainless steel tubing from the 4 locations to the 4 valves on the valve attachment plate. Very often this tubing is already existing. It just needs to be reconnected again. If you are interested in a detailed offer, here are our contact details. Back to the roots of furnace operation with base draft. An emission engineering device which allows you making your draft control smoother and safer.